Welcome back, class. Tonight we're going to talk about heat engine efficiency and the law of entropy. And remember, what we've learned already is that heat engines are a direct application of the first law of thermodynamics, when the internal energy of a heat engine is constant. And so we see that the work done by the heat engine is equal to the heat input minus the heat output. So today we're going to learn about how efficient that process is. And heat engine efficiency is defined as the amount of work the engine does divided by the heat input. And another way of thinking of this is, it's what you get out of the engine divided by what you put in. And of course we know that you're never going to get as much out of the engine as you put in. A lot of that heat is going to be exhausted to the environment as what we call thermal pollution. So the efficiency is the work done divided by the heat input, and that's what QH stands for, the heat input at the high temperature reservoir. Let's go ahead and do an example. A steam engine does 1,500 joules of work with a heat input of 4,500 joules. What is the efficiency of the steam engine? So now this is a pretty straightforward example. I could give you an example where maybe we didn't know the heat input, but we knew the heat output, and first you'd have to solve for the heat input before you actually calculated the efficiency. But here I give you the values straight up. So all we need to do is look at our formula for efficiency. It's the work divided by the heat input, and we plug in the values. The work done is 1,500 joules right here, and the heat input is 4,500 joules. When we divide those two numbers, we get a decimal of 0.33 or 33%. So this means that 33% of the energy we put into the engine was converted into work. So that's about average for a heat engine, or maybe even slightly above average. Most of our gasoline and diesel engines are about this efficient. Okay? So a lot of the energy, about 67% of this energy, gets exhausted to the low temperature reservoir, and that is the outside environment. And we call that thermal pollution, thermal meaning temperature. So this is going to increase the temperature of our environment just ever so slightly. Okay, now the law of entropy. And this is actually kind of a fun idea to play around with. And entropy is directly a measure of the amount of disorder. So the more disorder that a system has, the more entropy we say it has. And what's important to understand about entropy is that it naturally increases over time unless work is done. So in most natural systems, things become more disordered over time. Okay? For example, your bedroom. It becomes messy over time naturally until you actually go and do work. You apply a force times a distance and move different things back to where they belong. So let's go ahead and look at a couple different scenarios. So here we have some gas molecules that were pumped into a container. And we can see that these gas molecules are highly organized. They're all together in one spot of the container. But over time, we would expect that those gas molecules would spread out and be randomly oriented around the container. So let's look down here. Here we have a pile of bricks. Here's another analogy. A pile of bricks. Would we naturally expect the pile of bricks to become disorganized? Or would we naturally expect a disorganized stack of bricks, a jumble of them, to become a neatly organized pile? And of course, we would not expect a disorganized pile to naturally become organized in a pyramid. So time would actually be pointing to the right in this bottom example of entropy. So let's look at a couple more examples. So we already talked about the bedroom. Your bedroom naturally will become messy unless you do work to clean it up. Now our bodies, our cells in our body actually do work. They move around our body to maintain homeostasis. So that is basically to keep your body functioning properly. Your cells are constantly dying and being regenerated and moving things around your body. And so these cells are doing work to maintain this organization within your body. And as you get older, your cells are less able to do that. And your body actually becomes less organized, and homeostasis is not able to be maintained. And so eventually, when your body's unable to do that anymore, the body actually shuts down. And also, as it relates to what we've been learning about, energy degrades as it transforms from highly organized states to less organized states. And this occurs naturally. We take gasoline or wood or diesel fuel, and these are the energy in those different energy forms is very highly organized. Chemical energy is organized into bonds that are very easy to transport. We can transport fuel around the world. But when we burn that fuel, and that fuel becomes heat to expand a piston, the waste energy turns into thermal energy, which is these gas molecules moving all around throughout our atmosphere. That is very disorganized, as you can imagine. So liquid is more organized than a gas, and a solid is more organized even than a liquid. So we can see how the energy degrades as we use heat engines and burn the fuel to produce the work that we get out of them. So this has been a lesson about heat engine efficiency and entropy, and I will see you in class tomorrow.